Good morning, afternoon, evening, wherever you find yourself. We are going to start talking about logs today. They're fantastic. So let's just take a look at it. First, I want to tell you kind of where they came from. The story of log. This curve, you're going to learn how to graph this curve here later on, but not today. Um, Logs kind of fueled the scientific revolution back in the 16, 1700s, led to so much stuff in science and medical fields, and physics, and all kinds of things, chemistry. So, what logs are? And the same idea that multiplication is a shortcut for repeated addition here, like 8 plus 8 plus 8 plus 8. People got tired of writing that, so they're like, let's multiply. Multiply 8 times 6 is the same thing as adding 8 6 times. It makes it easier for us, it shortens so much work. Exponents, same thing. Exponents just mean, hey, take 8 and multiply it 6 times. Instead of having to write this out and work it out 8 times 8, then times 8, then times 8, we can just kind of figure out what 8 to the 6th power is. Logs, as weird and crazy and as stupid as they're going to look like to you, they are the same thing. They're just going to take exponents and sort of make shortcuts for us to do a lot of other things with them, especially when we have exponents like what we were looking at the other day in our variable. 8 to an x power equals some kind of a number. That's tough to deal with, especially if it's not a nice, easy one like, something that goes in nice and perfect. If it's decimals and other weird stuff, this gets really tough. And so, at some point, a long time ago, this guy, Mr. John Napier, and I'm not even going to try and say this guy's name right, but they both were sitting here and kind of playing around with numbers. This John guy, apparently, he was pretty big in his church life and everything, but he played with numbers on the side. And now he's known for all of his different innovations that he came up with numbers and shortcuts to things, rather than for his work as a religious scholar, which is kind of what he wanted to be known for. But anyway, they both came up with the beginnings of logarithms on their own. This guy in 1614, this guy in another country, at 1620. They kind of found each other and then sort of collaborated together. And then I think it was like 1624 came up with the basic notation of what we call logs today. And that led to so much other stuff. All this different scientific revolution things happened. People started to be able to get through numbers a whole lot easier. Instead of just huge tables of data on things, they could put them together, use logs to go through it quicker, and all kinds of different discoveries started to happen. Advancements in medicine and astrology, physics, chemistry, all kinds of things started moving forward. Um, so today, how we still use logs on basically an everyday type of life, payments on loans. When you start looking at buying a house or buying a car, your different payments with the interest rates and all that kind of stuff, those types of things are based on logs. Before calculators were around all the time, I remember my dad had a book that he had to look up, what kind of payments you'd be making versus different types of loan amounts. It was all log tables. Decibels, your decimal levels as far as how much you kids are killing your ears with those stupid headphones. Those are down over in this range somewhere where your ears are actually dying because you put your headphones on so loud. But the decibel levels calculations are all based on log tables. Brightness of light, this is how they figure out how far away stars are and planets and solar systems and things like that, as they use the light decimal levels or intensity levels and can tell exactly where things are and all that kind of stuff based on log tables. Your acidity scale, if you're over in chemistry class looking at how much of a base or how much of an acid is something, these numbers are not this simple, but logarithm basically made them so that you can use a 0 to 14 scale. The numbers go from huge numbers to down to decimals and stuff like that, and it's a mess. But the log tables kind of make it simpler, so you can make a nice, easy table like this. And yeah, so your chemistry class gets to think logs. Earthquake magnitudes. We haven't had a huge one in the last little while, but all the different earthquakes, when you talk about it's a 1.0 or 2.0, 3.0, that's all logarithmic. So the difference between an earthquake that's a 1 and a 2 is not the same as the difference between a 3 and a 4. The bigger that number gets, it starts to grow, ridiculously over exponents. So it's exponentially. and that's all based on log tables. Your CSI, when they talk about how they can figure out how long somebody's been dead, that's body temperatures, and that's logarithmic tables. Bacteria growth, when you're talking about spreading of different things, bacteria grows on exponential scales, which is log tables. Um, radio Radioactivity, things with nukes and nuclear energy. When they were looking in Japan a couple years ago when the thing blew up after the earthquake and tsunami and all that, how long it takes before people can be in there and be safe is all based on logarithmic tables of decay of how long it takes for the nuclear material to decay off and not be harmful anymore. Your Walking Dead style zombie apocalypse academic or epidemics, that's all based on log tables on how fast that'll grow. Calculus, when you guys, none of you probably will make it there, maybe in college, who knows. But calculus is all about figuring out the area underneath these curves, and doing that involves log all the time. Alright, so how we do this? What's going on here? Well, logs are basically here to try and help us out in this situation. 5 to what power makes 125? We're going to be looking at that chart that we were using last section on the very front page of your packet a lot today, so you might want to be able to reference that. So 5 to what power here, that's going to be the third power. 3 to what power makes that 243. If you go look on here, there's our 3, there's the 243, so that's going to be the fifth power right there. So logarithms. Log of 125 then is going to be able to save us and just say, well, that is 3. Log of 243 is going to tell us that answer is 5 based on those things that we just looked at. So 2 to what power makes a 32? Hopefully we're thinking, hey, that's 5. Well, then log of 32 is going to be 5. This is just another way to write this little problem. 4 to what power makes that 124? Let's see here. 4 going across 1024, so that's going to be a fifth power again. So log of 1024 is going to be 5. So we're going to keep looking at that table. Oh, goodness. What just happened there? Sorry about that. We're going to keep using this table all day, so you might as well, have that paper handy. 8 to what power makes that? That's going to be 4, so log of that number is 4. And you kind of get the idea of what we're doing here. 6 to the third power makes 216, so log of 216 is 3. So now we can just use the table and go back and, whoops, where's paste? There we go. I lost it. Yeah. So now we can just look through the table. 6,500, where do we see this number at? I don't know. Hey, there it is. So what's our answer going to be? It's going to be log 9 to the fourth power, so 4 is our answer. 729 here, where's that at? There it is. Alright, so that's going to be a cube power, so it's to the third. Alright, now our problem starts to rise of 16. Is log of 16. When you look at your table, you're going to see that that's happening right here, it's happening right here. So what are we going to go with? Are we going to go with it equals 2, or are we going to go with it equals 4? In these situations, that's when we have trouble. So what we do is we write our base down there a little bit smaller. So what happens here? That means log base 4 of 16, meaning we're asking 4 to what power is going to equal that 16? Well, that's 2, because 4 squared makes the 16. Log base 2 means we're saying 2 to what power equals the 16? Well, that's a 4, because 2 times 2 times 2 times 2 makes that 16. And that's how that's going to work for us there. 64 is even crazier. If you look at that table, we got 64 to a first power, 8 squared, 4 cubed, 2 to the sixth. All those make different ways to get to the 64. So we're going to put our base in here, and that means we're saying 8 to what power makes the 64. We're looking at this situation, and that's going to be 2. Alright. So basically what happens here is you've got log to your base. We're going to call this the answer equals your power. So your base to your power gets your answer. And it's just how we're going to write our logs every time. So here, our bases are going to be the 9 and the 8, because those are the little numbers here and here. It's just kind of base to this power is this number. 9 squared makes 81. 8 to the third makes 516. And that's what's going on here. So now our power. 11 to what power? 3 makes that big number. 4 to what power? 5 makes that number. And lastly, our answer numbers are always going to be these ones right here. So it's 49 and 27. 3 cubed makes 27. 7 squared makes 49. Alright, so rewriting things as an exponent. If we just kind of use that same sort of counterclockwise thing, 5 to the 4 equals 625. And then we're able to write it out. 3 to the negative 2 makes 1/9. Remember, 3 squared is 9, and the little negative throws it to the bottom of the fraction. So these things don't go away, they all stay here. So, still doing the same thing, here to here, and back again. 10 to a negative 1 is going to equal 0.1. Swoop around here, 1/4 to the negative 3 is going to equal 64. So again here, the negative is going to take the 4 and put it up top, and 4 cubed is 64. Alright, so now writing as a log. We're going to do the exact same thing anyway. Here, 4, 64, 3 is going to be how we're going to write it. So log base 4 of our answer, 64, equals our power, 3. So that same motion of just kind of going like this and writing your numbers that way is going to work for us. This to this to this. So we get log base 9 of 1 over 729 equals negative 3. Log base 10 of 1 with a lot of zeros. That's what, 1 million there? Equals 6. Did I get the right amount of zeros? There we go. Perfect, perfect. Alright, so now we're going to find our values of these different logs. And this is where we're going to start using our table a little bit. But the way you're thinking about each one of these is 8 to what power equals 64. So 8 squared. 3 to what power equals our 81. That's going to be to the 4th power. 7 to what power makes this big number here? That's 5. And if you're not sure on any of these, go check your chart. So 13 to what power is going to equal 1 over 169? Well, I know 13 squared is the 169, but since it's on the bottom, we're going to put a negative there. Whenever you see fractions kind of going back and forth, that's always going to get you your negative numbers. 10 cubed is 1,000, so 10 to the negative 3 is going to be 1 over 1,000. Alright, 2 to what power is going to make 16 is going to be 4, but if I need to go from fraction to number, I'm going to put the negative in front. Alright, 1/4, that'll be a negative 4 there, because 4 times 4 times 4 times 4 makes that. Negative flips your fraction. 14 to what power stays at 14? I hope you're thinking, hey, that's 1. 14 to the 1 equals 14. So 3 to the 1 equals 3. How do we get a 0? 5 to what power is going to equal 0? Or I mean equal 1? I give away the answer now. That's got to be 0. 5 to the 0 power is the only way to get 1. So whenever you have a 1 here in your log in your answer spot, that's going to be a 0. Alright, I hope you're not too confused. Just stay calm. Use your logs and you'll be okay. We'll start doing a lot more stuff with them on the next section. In any case, be well, stay safe, make good choices, use your logs.